Can somebody tell me what parameter this set of units would be describing?
Distance? No. Weight. Volume.
Density. The units for density have to be what? Mass divided by volume. And so there's a mass and there's a volume. So this totally is a density unit. This can't be anything except a density unit. Just like speed has to be distance divided by time. If it's anything besides that, then it's not speed. So what about this unit over here? It's still density, right? I changed to a different mass unit, but it's still a mass unit, so it really doesn't matter. So for this one, it was pretty simple. It was 2.34 kilograms per meter cubed. We left the meter cubed as is, and we're going to go and turn that into grams. So for every 1 kilogram, it's 1,000 grams. So the kilograms cancel out, and we end up with 2,340 grams per meter cubed. Do I put a decimal place after this 0 in the 2,340? Why not? You're right. It's not 3 sig figs, right? If I decimal placed after that 0, that's telling you that the 2, the 3, the 4, and the 0 are all significant, but from the problem, we've only got 3, so it can't be. How would it be another way you could write that? 2.34 times 10 to the third grams per meters cubed. That works, and then it's obvious because the 0 is not there. Okay, so let's do these conversions. Do you guys know what a furlong is? You do now? What did it talk about what a furlong was for? What is a furlong equal to? 220 yards. Yeah, 220 yards. Use? Nobody? What is 220 yards equal to in miles? Anybody know? A track, like a track that they're running on, how long is the track? 400 meters. How many yards? Nobody?
I'm kidding.
440. 440 is what a track is. It's 400 meters or it's 440 yards. So what is a furlong then?
200 meters.
220. So it's half a lap around the track. What's the one lap around the track is how many miles? So half a lap around the track is? So a furlong is? Eighth of a mile. It's just another name for an eighth of a mile. That's all it is. So we're going to go from these furlongs into meters. So it's 9.36 furlongs, and for every 220 furlongs, it's no, that's not right. For every 1 furlong, it's 220 yards. And then for every 1 yard, I'm just going to skip a step here and go 36 inches. And then for every 1 inch, it's 2.54 centimeters. And then for every 100 centimeters, it's 1 meter. And then all the units cancel out. We've got the furlongs canceling, and the yards canceling, and the inches canceling, and the centimeters canceling. The only unit we have left is the meter unit. And what'd you guys get for a number for this? Anybody?
95.6.
9.
No, sorry. Yep. No, furlongs in the meters. Sorry.
It's okay.
1880.
I'm just gonna look. I got that might be fine. We'll talk about it in a sec. I got that. Okay. How many sig figs for this?
3.
So my answer should be
1880.
1880 with no decimal place after the 0. I could have added an extra step here. I could have gone from 3 yards into sorry, 1 yard into 3 feet, and then 12 inches into a foot. But I didn't have to. That's why I said I skipped a step there. There are 36 inches in a yard, so 3 feet in a yard, 12 inches. So I did one little calculation in my head. Why am I doing this unit conversion right here? Because it's exact. What is the situation about sig figs with this, 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 and this? Do you need to consider significant figures with those things I just pointed to? You do not. Significant figures deal with what? What?
Like the question that's being asked, like the number that you're given?
No, I mean specifically, like in general, significant figures deal with what phenomenon? Say again? Sure, accuracy or uncertainty. Is there any uncertainty here? Now that you looked it up, there isn't, right? Is there any uncertainty here? So do I need to worry about significant figures here? No. Is there uncertainty here? Yeah, somebody measured this. This is not a measured value. This is a defined instance. Defined, this was measured to be exact, so that's okay. That is a definition. So these things don't have anything to do with significant figures, so I don't worry about significant figures with those fractions, those portions of the railroad track. I only have to worry about the one measured value. So that's why this is only 3 sig figs, which is why you need to use this one because it's exact. So if you use the 1 meter is 1.09 something, something, something yards, can't use that one because there's significant figure issues with that. You have to know what the sig figs are with that particular unit conversion, and then that might be less sig figs than this here, depending on which one you use. So if you don't want to worry about sig figs in your unit conversions, you need to use this one. All right, so we're going to go rods, hours, leagues, week. This, what is this unit? What kind of unit is this one and this one? They're very stupid speed units, right? It's a distance and it's divided at time, both of them are, so it's a speed unit, but it's nothing anybody would use. Leagues, do we know where this is used? Ocean stuff. How about rods? 16.5 feet. It's for draft of boats. So you're coming into port and you want to know if your boat is going to be able to pull up to the harbor or not. I was in the Dalles yesterday and I walked past the dock that they have there, and the river boat is docked up there. Why is it not docked up down here anymore? I mean, the Dalles is not the best touristy place on the planet, right? I mean, if you were a tourist, would you rather pull into the Dalles or Hood River? It's not even, there's no answer to that, right? It's Hood River. Well, why aren't they pulling into Hood River anymore?
You're talking about people?
Nope. I'm talking about the boat. Why does that boat no longer stop in Hood River? It's no longer deep enough. After the washout in 07 of Highway 35, the sandbar was created, and now that boat can't get in there anymore because the draft is too shallow. And a long time ago, the way they would check draft is they'd have a rod. They'd have several rods that they could connect. Each end of the rod had a little connection piece. So they could take the rod and drop it into the water, and it's 16.5 feet. They know the draft with their own boat, and then they could say if they could actually get in or not. And they can connect another rod to it and figure it if they have 31 or 33 feet of depth to go in. So it's an old time. It's before the whole like fish finder sonar stuff to figure out how deep the water is. So rods per hour, and we're going to go leagues per week. So I've got 5,632 rods per hour, and I need to get over to weeks. So I'll go 24 hours is 1 day, and 7 days is 1 week. And then I'll go 1 rod is 16.5 feet. And then there are 5,280 feet in 1 mile. And then for every 3 miles, there's 1 league. And so then we've got leagues per week. Number for that, anybody? 985.6, yeah. 985.6. 95.6. Is that good for our sig figs? 95.6? Yeah, I started off here with 4. They're all real numbers, so then my answer needs to have 4. So my answer has 4. Okay. Let's go on to the next one. All right, so we're going to solve temperature Fahrenheit out of this thing. What do you got to do first? Divide by 5/9? Sure. Multiply by 9/5? How about that? Multiply this side by 9/5. All that stuff cancels out. Multiply this side by 9/5. 9/5. And then I need to add 32 to this side, and then I can add 32 to this side. And I end up with temperature Fahrenheit is equal to 9 divided by 5 times temperature Celsius minus 30, plus 32. The top equation, the equation we started with, needs parentheses. The equation we just solved for does not require parentheses. Can somebody explain why?
Change in temperature is a whole times, like,
No.
you need the quantity before you times it by 5/9 in the top equation.
Okay, so why can't I just do that without the parentheses?
Order of operations.
It's all about order of operations, right? If you do not include the parentheses in this calculation here, what's going to happen mathematically with your calculator? It's going to take 32 times 5 divided by 9, then subtract that value away from whatever your temperature Fahrenheit is. That can't happen. To do this calculation, the first thing I need to know is whatever my temperature Fahrenheit is, then hack off 32. Then I can multiply by 5/9. So why is there no need for parentheses down here?
Because it's in order of operation already?
The order of operations, it doesn't really matter. It's going to do these 3 things before it's going to do the plus 32 anyway, so I don't need to put a parentheses around that. So just make sure you're careful when you're going from Fahrenheit over to Celsius, and you take that 32 off before you do the calculation. All right, let's do this conversion. So we're going from Fahrenheit to Celsius and then to Kelvin. So I'm going to go, my temperature Celsius is equal to 100 degrees minus 32 times 5/9. So somebody have a value for that? 37.8 degrees Celsius. Is that enough? 37.78? Why? There's 4 sig figs here. Do we see this as 4? Nobody would have written that 0 there unless what? Unless the thing they were measuring actually said 100.0. If it only said 100 and stopped right there, then they would have just written 100. So this is a 0 to the right of the decimal place, so you got to count that. All right, so there's my Celsius, and then to get my Kelvin, I'm just going to add my 273 to this, and I get 310.78 Kelvin. So 310.8 Kelvin. Is that right?
1.9. I think I did the 273.15.
Oh yeah, if you throw in the 1.5, then it would go to 8. Yeah, I don't have that in there yet, but it could be 1.5. Okay, so to convert the Kelvin, you actually need to go into Celsius first, right? There isn't a conversion to go straight from Fahrenheit into Kelvin. Question, does this number right here make sense? Why?
Body temperature is 98.6 and you want to get at 37 degrees Celsius.
Celsius body temp is 37 and Fahrenheit body temp is 98.6. Well, that's pretty close to 98.6, right? So whatever my answer is, it's got to be somewhere pretty close to 37. If it's not really close to 37, then I made a mistake. If it's like 137, then I obviously made a huge mistake because that person's boiling. Way past boiling, actually. So when you're doing these calculations, there should be about 4 Fahrenheit or Celsius numbers you should know. Did we already talk about this? What are the 4 Celsius numbers, temperatures you should have in your head? 0. What else? 100. What else? 37. And what else? About 20. What's about 20? It's about room temp. Okay, so then you kind of get a feel for, you're looking at a thermometer, if it's room temperature-ish or not. So if you know it's 60-something degrees, then you can kind of figure this out. I think actually the next problem deals with that. Let's look at the next one. Okay, so I'm going to go from Kelvin into Celsius. So the first thing I'm going to do is subtract off 273, and then I'm going to get 17 degrees Celsius. Okay, so 17 degrees Celsius. So your Fahrenheit number should be somewhere around what? Somewhere room temperature, 60 something, mid to high 60s, something like that. All right, so let's make sure that works out that way. So 17, and then I'm going to multiply by 9/5, and then I'm going to add 30. No, I did that backwards, didn't I? Did I do that backwards? No, I didn't do that backwards. Plus 32. So what's this guy work out to be? 17. Times 9 divided by 5 plus 32. Oh, you're not working. 17 times 9 divided by 5 plus 32. Got 62.6 degrees Fahrenheit. I've only got 2 sig figs, so then my answer is going to be 63 degrees Fahrenheit. I only have 2 because there's only 2 right there. So the 63 makes sense? Okay. All right, next one. When you think about density, or if you're going to describe density to somebody who isn't taking a science class, how would you describe it? Maybe to like a 5-year-old.
Density is determined by how squished together the substances.
I like it.
Condensed food that will get the less.
Squished is good. Squished. Somebody else got something else? Thick?
Yeah.
No, thick is a distance. That's not going to work for us. Compressed. Compact. I like how tightly packed. So how tightly packed the atoms are if it's an element, or how tightly packed the molecules are if it's compounds. We okay with that? So what metal would have tightly packed atoms? Gold, osmium, those kind of things. And an element or a metal that has loosely packed atoms? Aluminum, lithium, those metals have loosely packed atoms. All right, so for this next question here, can you answer the second portion of the question before you do the first part? Anybody? How about yes? Why is yes the right answer? Mass, volume, smaller number, bigger number. So what's my density going to be for this? Less than 1. So I can already tell you right off the bat that this thing's going to float in water because it's going to have a density less than 1. So then we can knock out 240 grams divided by 268 centimeters cubed. And then we get grams per centimeter cubed. So that's going to be a density, and it's 0.9 or something like that? 0.90. I feel like that's what it is, 0.90. I have 2 sig figs with the 240, and this is like 0.89 something, and it rounds up to be 0.90. So this is telling me 2 significant figures, correct? You okay with that? So this one was probably one step harder than it actually wanted to give you. Sorry about that. I gave you this problem hoping that you would look at the notes and then attempt to do the specific heat problem, but I probably should have given you one step easier than this one. Not that this is super hard, it's just a little bit of algebra. The equation is Q is equal to MC delta T. The Q is heat, the M is mass, the C is the specific heat, and the delta T is my change in temperature. And do we remember what the change means, the delta actually means in math? What does it mean always? Final minus initial. So this delta is always going to be final something minus the initial something. So we could be talking about your checking account over the course of the month of September. So what was the initial amount? What was the final amount? So I take my final amount, subtract off my initial amount, and that will tell you what your change is for the month. So maybe you started with $600 in your checking account, and at the end of the month you ended up with 550, so your change would be negative 50. That makes sense? You have $50 less than you did at the end of the prior month. So in this case, we're going to be talking about temp. And so what piece are we missing? So this is a parameter, this is energy, this is a parameter, mass, this is a parameter, the specific heat. And then this parameter here is actually divided up into these two pieces. So which one of these don't we know? Our final temp. Okay. So I'm looking for a temperature, correct? And if you're in that the next page on the notes, it gave you a specific heat value for, we're talking about glass, right? Yeah. So the specific heat value for the glass is 0.22 calories per gram degree C. And then I have all this other information. I need a number that's got a unit of degrees Celsius. This is calories, this is grams. Here is a degree Celsius unit down here. So I'm going to use that in a railroad track. I'm going to say, true, but that was the initial temperature. We need to find a final temperature, right? So what I'm trying to calculate at this point is what my change in the temperature is. And then I can do the subtraction to figure out what my final temp is. And so then this is 0.22 calories. So if this is the value that you would get out of the book, is it okay for me to flip it over? Why is that all right? Give me an example of how you know that's okay. Yeah, a foot is 12 inches, whether it's in the numerator or the denominator. So same situation here. So what I'm going to do is now I need to get rid of the grams and the calorie part. So I'm going to put 3750 calories here, and my gram is 675 grams. So the grams cancels there, the calories cancel there, and the only unit I have left is this degrees Celsius. I think it's a stupid number, like 1.17 or 1.10 times 10 to the 7th. Is that right? Actually don't have it in there. So 3750 divided by 675 divided by 0.22. Oh no, that's not done. That's normal. That's 25. Is that right? 25. I'll say 25.3 degrees Celsius. So what did we just calculate? We calculated the change, right? So this is like the final balance at the end of the month in your checking account. This is the final temperature of this piece of glass after I've added this heat to it. But this is the change in the temperature. So what's the final temp going to be equal to? This value plus whatever I started with. It started at 15 degrees, and I increased the temperature 25.3 degrees, so then my final temp is going to be 40.3. So I've got this temperature equation here, temperature final, temperature initial, And so I'm looking for my temperature final, and so that's gonna be equal to my change in my temperature plus my initial temperature. So I got 25.3 degrees C plus 15 degrees C, and we end up with 40, and I'm just gonna put a decimal there, degrees C, because we have 2 sig figs here. So then my answer is gonna have 2 sig figs in it. So even though it's 40.3, I'm gonna have to drop that 3, and there's my final temperature for that.
So,
Yo.
can we just use the equation in the book?
Oh, totally. But, yeah, that's totally fine. I just never use any equations. Okay, so this question, I'm trying to get you to think about the differences in terms of like how much bigger one object is than another object. So you didn't actually need to do any math associated with this. What we're trying to do is compare the bug and the truck to each other. So if I'm talking about kinetic energy, the kinetic energy is 1/2 and then mass and velocity squared. So what I've got is a 1/2 mass and velocity squared for the bug, and I've got a 1/2 mass and the velocity squared for the truck. I'm going to compare these two equations to each other. What can I get rid of right off the bat? No, I can't. Well, I'm sorry. Yeah, I was thinking something even better than that. How about get rid of the half? Right? They both have the constant of 0.5, so let's get rid of that thing right away. So now I'm still comparing these two equations, and so I'm looking at this velocity and I'm looking at this velocity, but the velocities are the same, right? So we can also cancel that out. So now I'm comparing just the masses, and this one's mass is twice the other one's mass. So then what's the kinetic energy difference between the truck and the bug? So the truck is double the kinetic energy. All right. So now let's do this problem again, except this time the bug is going to be moving faster. So I'll do 1/2 mv squared and 1/2 mv squared. And we know that it's the same truck, so it's double the mass here. Oh, let's get rid of that half. The half's gone. We're going to compare the masses, and we know that the mass is double for the truck, but the velocity over here for the bug is double, right? But that doubling of the velocity, it's not just twice as big, is it? So that 2 is controlled by the exponent 2, so this turns out to be a 4. So this works out to a 4. So then my answer, I've got a 2 over here, and I've got a 4 over here, so what's my answer? The bug is twice as much energy in this particular case, right? So here's an instance where you'd rather be hit by the pickup truck than by the VW bug, right? And then the last one, you'd rather be hit by the bug than the pickup truck. Not that you want to be hit by a car, but whatever. Calorie definition. That's it. It's the amount of heat needed to raise the temp of a gram of water a degree Celsius. So is it very much energy? How much water is a gram of water? A milliliter, which works out to about 20 drops. So if I increase 20 drops of water 1 degree Celsius, then that's my calorie unit. This is how people figure out the number of calories in a particular foodstuff. Does anybody know how that works? How do you figure out how many calories are in a piece of Wonder Bread? Sorry again? They take a gram and they put it in something, a chamber that measures temperature, and they let it catch on fire, and then they measure how much how much heat's been released. And a really easy experiment that I think we did in 5th grade is we took a peanut and we stabbed it with a paper clip, and we put it, I think we had 50 grams of water inside of a soup can, an empty soup can, and then we lit the peanut on fire. And then we put the peanut underneath the soup can, and we measured the temperature of the can of water, how much the water went up, and that told me how many calories was in the peanut. It's not the best way because some of the heat's leaving on the sides, right? The best way is to use the apparatus called the bomb calorimeter, which is this huge, or not huge, but it's this really thick-walled steel container that doesn't let any heat out. Everything is stored inside. But that peanut actually worked out. It was like, doing that experiment in 5th grade, we were like 7% off of what the actual calorie you would find in a particular peanut was. So it's literally, they just burn the food and see how much energy comes out of it. That tells them how much it's supposed to be giving you. Okay, that is it.